Hey, Dr. Clark here with you again, and in this video we're jumping into Chapter 8, learning how to do inference with multiple proportions. Let's get started. So, Chapter 8 is really an extension of Chapter 5, okay? In Chapter 5 we learned how to do inference with two proportions. I think one of the examples we did was the explanatory variable with did people swim with dolphins or not, and then did their depression improve or not. So there was a certain proportion of people who improved, and that proportion was different depending on whether they swam with dolphins or not. So that was kind of the setup. So we had two proportions. We were comparing them. Were those two proportions the same or were they different? And in Chapter 8, what's going to happen is the explanatory variable will just have more than two choices. So maybe it was whether they swam with dolphins, whether they swam but not with dolphins, or maybe they didn't swim at all. Maybe there was three choices, and then we checked whether their depression improved or not. Or maybe, you know, freshman, sophomore, junior, senior, you've got 4 years, and then we look at the proportion of students who live off campus or something. Is the proportion of students who live off campus the same or different depending on what year, you know, students are? So the response variable is still some sort of yes or no, but the explanatory variable just can have more than two choices. All right? And in this section, we're going to do a simulation-based approach, and then in the next video, we'll do a theory-based approach. Okay? And so when you look at this, what's going to happen is instead of just having two proportions and you're saying, hey, is this proportion the same as this one, or are they different? There's just going to be 3 or maybe even 4 proportions. So there could be another row or another column here. And then now we're saying, like, are they all the same as each other or are they different? Okay. When we set up our hypotheses, instead of just having pi 1 and pi 2, the true proportion for group 1 and the true proportion for group 2, there could be a pi 3 and a pi 4. So we call this multiple proportions. We're still looking for an association between an explanatory and a response variable. And for our null hypothesis, before we always just said pi 1 equals pi 2. Well, now we have to say that all the proportions are the same. So if there's no association between the explanatory and the response variable, then the proportion of success for each of those possible choices in the explanatory variable should be the same. So pi 1 equals pi 2 equals pi 3 equals, etc., depending on how many choices there are for the explanatory variable. You know, freshmen, sophomore, juniors, seniors, etc. And then the alternative, if there is an association between the variables, then one of these proportions must be different from the others, or at least one of them. And it could be that 2 of them are the same, but one of them is different. So that's the kind of thing we're looking for. So we just say at least one proportion is different from the others. And we usually write that out in words because otherwise you'd have to say pi 1 not equal to pi 2, or pi 2 not equal to pi 3, or pi 1 not equal to pi 3, or pi 1 not equal to pi 4, and it just gets a little bit silly. So we just say all the proportions are the same, or at least one proportion is different from the others. When we get data, so our hypotheses are about the true parameters, right? The true population proportions. The data comes from a sample, so we get statistics. And the question is, are the statistics the same as each other or different? And moreover, are they different enough that that would give us evidence that the true population parameters are different? So, you know, maybe this is sample data here and you say, oh, okay, well, these are different, but are they different enough to say that the true proportions are different from each other? Or is it just not strong enough evidence? So we want to quantify how different are these sample data. And the way we do that is through something called the MAD statistic. MAD stands for mean of the absolute differences. So what we did when we had two proportions was we subtracted them. If they equaled 0, they were the same. And if they didn't equal 0, they were different. Well, now we have more than two proportions to look at. We got P1 and P2. We got P1 and P3. We got P2 and P3. We could have P1 and P4. So what we're going to do is we're going to subtract all of these, all the possible combinations, and that'll give us a bunch of numbers. And some of them could be positive and some of them could be negative. So we're going to take the absolute value. So basically make all of these differences into positive numbers and then add them up and average them. Okay, so it's the average or the mean of the absolute values of the differences essentially. And because we're looking at differences, the bigger the differences is, when you add these up, they'll get bigger and bigger and bigger. So the more different the proportions are from each other, the bigger this MAD statistic is. And so this MAD statistic is a way of combining all of the different differences together into one single number. And the bigger the number is, the more different these p-hats are from each other. If all the p-hats were the same, then all the differences would be the same, and this would be 0. Okay, so the bigger this MAD statistic is, the stronger the evidence that the true parameters aren't equal. All right, and then we'll have to simulate. So we'll have to do a simulation to see what kind of MAD statistics you could get if there really were no association. All right, and then we'll compare our MAD statistic that we got from our data to what could happen by random chance. And then we'll see if our MAD statistic is in the tail or not, and that's how we'll get our strength of evidence. So that's the main idea of what we're going to be doing with multiple proportions. And in the next video, we'll do an example, and you'll see exactly how to do it for a particular problem.